All right, I want to walk through a quick demo on the microcode machine. And this is a working version of the microcode, so we can look at something. And I'm going to actually set up both a test case that sets some code, and we're going to run that code and use our logic probe in the microcode machine to get an analysis of something. How often is memory over here, main memory, that's the gray box kind of in the center, actually accessed? So let's first of all set up a test, and when we do a test I can say that I want to do, let's do this load store halt test. That's the instructions. It does a load, store, and a halt, and that's going to overwrite what's in main memory with that instruction. And then let's turn on the logic probe to look at a couple different lines. The memory read, and if I can find it, oh, I did the memory write and the memory read. Now the logic probe is down at the bottom. It's partially cut off, so you're only going to see some of the lines here. But it's going to show us when memory was actually accessed in this by doing this. Now I can step through the microcode ticks. This is each time a microcode instruction is run, and walk through these one tick at a time. And each tick I'm seeing which lines are turned on and what happens. In this first tick, the PC 0 address is output. It goes on the bus. That's over here at the right in the center. And then it goes down here to the memory address register. In the next tick, we do a read. You'll notice that the read line is on, and down in the logic probe, we show a high for the read because that's the one we're looking at. In the next tick, okay, we've gotten the output from this, but memory is idle again. It's neither being read nor written. Okay. In the next one, we've got an instruction, and we've turned on a bunch of decode lines that are going to the decoder mux. That's the little red triangle. You'll see that in the center it says 1-1. That's line 1-1, which is the green line coming from the instruction register. So basically, it's taking the output from the instruction register, which happens to be the operand, okay, or the instruction, actually. It happens to be the instruction, and it's decoding that, and it's sending that out as some information to the microcode PC. We've got a load on the microcode PC, so this is where it jumps to the correct instruction to execute. We do another tick. It is now loading the memory address register. This is a load instruction, is load of address 3. So it's actually put address 3 on the bus from the instruction register, and it's put that in the memory address register. And now finally we have another memory read. This is memory read address 3. Okay. It's transferring the data from there to the AC. So we've got hex 1230 on the bus. And now we've got an output again from the PC to get the next instruction. Apparently we finished that instruction. So over here in the top left, you'll see it's back in a fetch state. I'll step to the next one, and yes, at address 1, we're fetching the next instruction, which is a store instruction. And we had another memory read down here on our logic probe, so this is the third one. And again, we're doing the decode that is allowing us to load information, and we've finally gotten a third instruction, which is a halt at address 2, and you'll notice the little red halt light is on. Now during all of those, if you were counting, my count is that during that entire process with 2 instructions, a load and a halt, that we actually used the memory, I believe, 5 times for reading and writing. And all of the rest of those times, the memory was actually sitting there idle. So 2 observations from this. Most of the time, memory isn't doing anything. It's just sitting up there using up electricity and idle. So if we could do something to use this is something like a DMA controller, then suddenly we're going to get a lot more utility out of our memory. We're going to use it more efficiently, because we can take those cycles where it is neither being read nor written, and we can actually do something with the memory. The second observation is, you notice how most of the time as we walked the PC through, it went to the next instruction. So if you had a smart cache that would go out and prefetch the next thing, so when you fetch an instruction, immediately it goes out and it gets the one immediately following this or the next few instructions, so that it doesn't have to go back to memory again to get instructions, then we could get the instructions from the slower memory into a faster register and take less time to execute each instruction. So these two things come directly from just observing and watching what happens, even on a simple processor like this. To give you some idea, normally when the x86 processor in like your PC or your Mac does a memory fetch of an instruction, it actually reads not just that instruction, but the next 128 instructions in a burst that it brings into a cache, the level 3 cache, so that the memory is now freed up for a much longer time and it's in a faster memory. Then it transfers the instruction you want into the level 2 cache, and finally into the level 1 cache so that it can start executing it. But in each one of these cases, each one of these caches is getting faster and faster, and most of the time the memory is idle, even though it went out and read a whole bunch from the memory all at once. So looking at the microcode, even with a simple 3 instruction, we can see why the memory is idle, and we could actually count the exact number of cycles. A processor designer will go out and actually mathematically model this against huge amounts of code and say, for all these different code bases, like we know what the Windows kernel looks like and the Unix kernel and applications like GIMP and Photoshop, they'll actually go and run these and they'll mathematically model how much of the time is the memory busy. How can I optimize my path from the CPU to the memory and back, and how big should I build the caches so that most of the time, not just the next instruction, but the next few instructions are on hand once it starts fetching things. So that's kind of my little condensed, this is what you see when you look at how memory is used and why we have things like instruction prefetch. Instruction prefetch means that not just the processor is using it better, but once we have these caches in between, we can make it run instructions much, much faster, probably an order of magnitude faster once the instruction is prefetched. Now, the downside to a prefetch is that this adds a behavior that can be observed. Some of you will remember that there were some very vicious defects that were found in Intel and AMD hardware that had to do with being able to tell what instructions it was running and how frequently based on the timing of the instructions. The things that they're looking for is if I'm running things and I can observe how fast they run, then there's this side channel attack of what speed at which they run, so that you can actually look at the timing and infer what instructions were being run, because now you can see what's in the cache and what isn't. Not directly, but just by the timing. And it turns out that it isn't just timing. You can also look at the power consumption of the system and say, okay, based on how much energy it's using, I can tell whether or not it had to go to memory and fetch this or not. And you can see into the interior of its processing and infer its operations.